All right, hey guys, you're now officially ahead of the other section by a little bit, so we didn't get to this on Wednesday, so you can be happy that you'll be 5 to 10 minutes ahead. I wanted to just spend a brief instant talking about a piece of biology that I think you're pretty used to. I think I've seen you doing gel electrophoresis in with Mr. Fusco, and maybe you did it with Mrs. Alvarez last year also. So obviously you can't tell me what it is, but think in your mind's eye, or picture the electrophoresis in your mind's eye for just a second. Freshmen are finding it interesting that I'm talking to myself in here. Alright, so you have this gel, and the gel is really just a medium for the electric field that you've applied across your tray. And then you put charges, you put your DNA fragments into there, and those DNA fragments are going to be influenced by the field, right? If they're negatively charged, which is I think what you're taught, they're going to move against the field, and then the larger fragments probably don't have more of a charge, but the larger fragments are going to have a smaller acceleration. They'll have a smaller acceleration, but more importantly, they have more resistance as they move through the gel. Right? So there you go, you've been using electric fields all year and you didn't even know it. Alright, so the last piece that I wanted to get to with you guys today is where the heck charges come to rest when we place them on a conductor. Hollow conductor, solid conductor, it actually makes little difference. So all I have up here is a sphere. I do want to concentrate on spheres for a minute. This approximates a sphere. Let me just check and make sure you can see that. Oh yeah, you can see it good. Now this actually is a very conducting sphere. I don't know what it's made out of. It might be made out of brass. So let me charge this thing up. I'm only going to give the PVC one little rub. So I didn't put too many charges on there, but there's at least tens of thousands of extra electrons I put on here. Let me touch here, and let's imagine that just 5 electrons went on there. Okay, so I put 5 extra electrons at one spot on the conducting sphere. So those electrons have some extra electric potential energy right now because they're so close to each other. Right? Each electron is exerting a very small electric field, and each electron will feel the electric fields from the other ones. So those electrons are going to move away from each other because nature minimizes their potential energy. Right? So those 5 electrons are going to redistribute themselves, or at least cause other electrons to move, so that they're essentially as far apart as they can possibly get. So maybe there's one up at the North Pole, maybe there's one at the South Pole, maybe there's one over here, and then the 5th one will be back on the other side. Okay? So that should be the lowest potential energy state for each of those electrons. All right? And then if I put more electrons on there, right, let me rub it a whole bunch this time. Right, boom, there's 20,000 extra electrons I just put on. Boom, there's another 20,000 extra electrons I put on. Those electrons are going to distribute themselves as far apart, so that they're as far apart as they possibly could be. All right, I hope that makes sense. All right, so on a spherical conductor, right, we're going to have a uniform charge distribution everywhere along the very outside of the conductor. Now this happens to be hollow, or essentially hollow. If this was solid, it would be the same story. We wouldn't have any charges residing on the inside of the sphere, right? Because they can get further away from other charges if they go all the way to the outside. Okay, so hollow conductor, solid conductor, all of the excess charge lies on the very, very, very outside. In your textbook, I think, maybe not. They talk about, let's say your car gets electrified. Maybe you run over top of some downed live wires. Maybe your car gets hit by lightning. You're going to be fine. That charge is not going to make its way to the inside of the car, because even if your car is charged up, all of the charge will be on the very outside. So the only reason you have a problem is if you like tried to get out of the car and you ended up touching the outside of the car, that would be a problem. Or if you kind of reached your hand out the window and then touched the outside, that could be a problem. But as long as you're on the inside, you should be fine. Yeah, so actually that's what I had in the next page of the notes. All right, so this car, I think this was a simulation, but we have the car getting hit by lightning. They're actually showing that we are discharging through the tire. There's a big enough electric field that we could charge by lightning, right? But any of the residual charge on the car should be on the very outside. All right, so that's good for a sphere, but most things aren't spheres, right? Most things are rectangles or cylinders or, you know, pointy parts like the dissecting needle. And then we don't have a uniform charge distribution. So on a sphere, this time we have positive charge, not negative charge, but whatever, same deal. The charges should uniformly distribute themselves. On a pointy thing, so here we have a half sphere, half pointy thing. There should be more charge at this extreme point. And the reason, and I actually don't think they drew this very effectively. We're going to have the largest amount of charge right at the point, and we shouldn't have uniform on this whole conical part. And the reason I think we should have more charge on this point is that, I mean, this is positively charged. Let me move over here, right? This is negatively charged. In fact, let me get that whole positively charged one out of the frame here. All right, I don't know, when the projector is filmed, it actually doesn't end up then projecting that very well. But we have this again, half sphere, half cone, but this time it's negatively charged. The electrons over here are so far away from the ones over here, right, that we end up having a bunch of ones that if this was a sphere, they would have lived over here, but they can get so much further away over here that we end up getting a whole bunch more electrons going in that region of our shape that gets them super far away from everybody else, right? So the potential energy of these ones should be the same as the potential energy of these ones, but we should have more charges there. I'm not sure that came out right. I don't think I need to finish that thought right. So pointy bits should have more charge than rounded bits, and because they have more charge, the electric field should be strongest at the pointy bits. Okay? So this is actually the same figure as before, but again, electric field at this most charged place should be stronger than the electric field at the rounded parts. So then you know what, we'll do lightning rods together next time, I think. So if there's still time in the period, and I think there should be because we did have a quiz and stuff in the B-Day section, maybe, you know, you guys can address some points of confusion with Dr. O. If that doesn't work out, all right, your homework. I'm realizing now that you're only looking at a very small part of the screen. If that doesn't work out, if either you don't have any points of confusion or if maybe Dr. O isn't the one that's with you, you're welcome to get a head start on the homework. Remember, you guys are due for a quiz next time, and then we do have our mega quiz on June 4th. All right, so I hope things went okay today. I know I went pretty fast in some of the parts of the lesson, but I'm trying to get you guys a few review days before the final, and it's not a given that we're going to have that. All right. Hope you had a good period. I'll see you guys on Monday.